Good morning, afternoon, or evening to everyone, and a very warm welcome for today's webinar titled Cultural Heritage Mapping and Monitoring. My name is Mladen, and I'm pleased to be your host for this, I can say, inspiring session. And today's webinar brings together experts and researchers that are dedicated to our cultural heritage understanding and preservation through the lenses of the geospatial technologies. So before we get started, just a brief reminder to all of you that this session is being recorded, and it will be made available online after the webinar. And please feel free to use the question and answers box through this session to share your questions. We will try to address as many as we can during the discussion part. So before we start with the official part of the webinar, I will just make a small introduction with the presentation about the schedule of the webinar and also about some journals introduction that are also related to the webinar. Let me just share my screen. Probably many in our audience are familiar with MDPI, and MDPI is present in the publishing community since 1996. It is an institute which has a mission to foster open scientific exchange in all forms and globally across different disciplines. And today we can probably say that we have 450 open access journals, and some of them are really top journals in their area of expertise. And we have a lot of our editorial board members involved in those journals procedures who shared our mission to foster the science all across the world. The journals related to this webinar today, we have 3 journals: Drones, Remote Sensing, and Heritage. And you can see that all of those are international peer-reviewed journals and open access journals, of course, related to different topics. Drones, journal focus with some basics like design and application of drones, and going through different applications of UAVs and different marine, water, underwater, remotely piloted aircraft systems. When it comes to remote sensing, it is also covering some fundamentals like sensor designs, their calibration, validation, and going through, again, different applications of remote sensing technology in different areas. And in the end, we have Heritage Journal. It is our journal that is focused on cultural and natural heritage science, and also different applications that we could use for better understanding of and preservation of our heritage and culture. This would be the schedule for today's webinar. However, I must highlight that there is one small change, and you can see this part where Marina Royer will present who is the Coastline Project Officer. She will talk about promotion of MSCA program and staff exchanges, and there is the change because that presentation will come first. So we will have this presentation first, and after that we will follow the schedule that you can see here. So once again, Marina will go first with her presentation, and after that we will follow the initial schedule that we have. This is a relevant special issue for today's webinar. You can see it here. You can see the title, the basic information about it. I will again share that information during the webinar in the chat, so pay attention to it. I will not bother you and take much of your time in the beginning. So this is just for your information, so you know that there are relevant special issue and also relevant papers that are also related to this webinar. Again, I will share all this information during the webinar in the chat, so you can have an access to these articles. Again, I'm inviting you to use the question and answer box to ask your questions. As you saw in the schedule, we will have two portions of this webinar with a short break in between. So after each portion, we will have a question and answer section around 10 minutes. We will try to answer as much as we can. And again, please use this question answer box and don't forget to address the question to our speakers just so we could know to whom are you addressing with the question. Our chair today will be Dr. Apostolos Papakonstantinou. He's from Department of Civil Engineering and Geomatics, School of Engineering and Technology, and from University of Technology in Cyprus. So that will be all from my side. I will now give the floor to our chair to also make a short introduction. And again, please feel free to ask questions and also pay attention to the chat and pay attention to the messages that we will be sharing. Thank you very much, Dr. Papakonstantinou. The floor is yours.
Okay, thank you all for joining us, for joining our workshop with the topic of cultural heritage mapping and monitoring. Today, we're trying to explore how modern geospatial technologies, including UAVs, photogrammetry, and other methods, remote sensing, of course, will revolutionize the way we document, preserve, and monitor cultural heritage. So from our point of view, we bring together researchers and academics in this session working at the intersection, let's say, of heritage conservation and spatial science to share methodologies, tools, and real work applications. I would like also to thank our presenters that I'm very sure that they are going to present very, very interesting topics and research. So also I want to thanks Remote Sensing Journal from NDPI for co-hosting and co-organizing this webinar. And of course, our media partners, Drones and Heritage Journal. So regarding the topics, we have applications of Earth observation in monitoring cultural heritage, geophysical methods for mapping submerged and coastal heritage sites. So we are going to deal with challenges in the coastal bathymetric mapping and water refraction effects. We will present you research on how to integrate multi-source geospatial data for cultural heritage documentation. Of course, we are going to present also drones in cultural heritage visualization and mapping. And finally, we will give you a presentation on virtual and augmented reality for immersive heritage interpretation. But as Vladen said, first we will have a short presentation for Marie Curie Staff Exchange Program for Funding Opportunities and Open Science Principles from our project officer, Marina Roger. So these are our keynote speakers. There is a diverse academic profile. As you mentioned, as you can see to our presentations. So I will thank all of them again. And I believe that you will see a lot of interesting things and in high research results from all of them. So as Vladen said, this session will be recorded for documentation and training purposes according to Coastline Project. So I think, thank you, and I think, Marina, we can start. So the floor is yours.
So my name is Marina Rogier. I'm a project officer working in the European Commission Research Executive Agency, and I'm project officer for Coastline Project. And in this presentation, this is a promotional presentation, let's say, you will learn a little bit about our action, what it covers in terms of funding, research, exchanges, and also in terms of eligibility for this action. As I said, this is a promotional video, So it will be my colleague of mine, Sandra Pintermarch, who will be speaking, and I just provide you with the updated information for the current call, which is now open, and it will close on 8th of October. Not very soon, so maybe at the end of the presentation, you will be interested to submit your proposal. So let's go on.
What is the Staff Exchange's Marie reaction all about? Horizon Europe is the current EU funding program due to last until 2027. It is organized into 3 pillars, and the Marie Skłodowska co-reactions, or MSCA for short, can be found under Pillar 1, alongside the European Research Council and the research infrastructures. There are 5 Marie Skłodowska co-reactions. They are doctoral networks, postdoctoral fellowships, co-fund, MSCA and citizens, and staff exchanges. Today's presentation is focused on the staff exchanges action, which is perhaps the least known of the 5 MSCAs. Staff exchanges focuses on equipping researchers and organizations with new knowledge and skills through mobility and training. In the previous 2 calls of Horizon Europe, the success rate for those applying to the staff exchanges call for proposals stood at around 40%. Whereas for other types of MSCAs, such as postdoctoral fellowships and doctoral networks, the success rate was around 13%. The main characteristics of the staff exchanges include aspects such as a bottom-up approach that allows applicants to freely choose the topic of their proposal across all scientific fields, the mobility of staff between participating organizations, which is the means through which the action funds knowledge transfer, and the stimulation of collaboration between institutions from the academic and the non-academic sectors, including many SMEs. Ultimately, the staff exchanges action promotes international, intersectoral, and interdisciplinary exchanges through the mobility of research and innovation staff on secondment from one institution to another. The minimum conditions when forming an MSCA staff exchanges consortium consist of 3 elements: the number of organizations or legal entities, the country they are based in, and the economic activity sector they are part of, academic or non-academic. A consortium must be composed of at least 3 legal entities independent of each other. The participating organizations should be established in 3 different countries. At least 2 organizations must be located in different EU member states and/or Horizon Europe associated countries. In what concerns the sector of the participating organizations, for those consortia composed of organizations exclusively established in member states or associated countries, at least one organization should belong to a different sector, academic or non-academic. The definition of academic sector includes the public or private higher education establishments awarding academic degrees, public or private non-profit research organizations, and international European research organizations. The non-academic sector comprises any socio-economic actor not included in the academic sector, while fulfilling the requirements of the Horizon Europe rules for participation. For consortia composed of organizations belonging exclusively to one sector of activity, all of them being either academic or non-academic institutions, as is shown on the slide, so long as one of the organizations is based in a third country, the consortium will still be eligible. Above these minimum requirements, additional organizations established in member states or associated countries and/or established in non-associated third countries can participate under the conditions provided by the Horizon Europe rules for participation. There is no predefined size for staff exchanges projects. Based on previous calls, the average size of the consortia is between 6 to 10 organizations. As for the number of associated partners, it should remain reasonable and commensurate with the size of the network. Secondments are at the core of the staff exchanges action. The transfer of knowledge takes place through the detachment of staff members between two organizations. During the secondment, the staff member involved acquires new skills and knowledge while working towards a particular set of project objectives, culminating in the production of specific deliverables such as prototypes, reports, etc. Upon the return to the sending organization, the staff member transfers the knowledge to their employer and colleagues. The mobility of the research and innovation staff between participating organizations is crucial for the staff exchanges action, and it is that mobility that triggers the EU funding for the project. Concerning those staff that are eligible to be seconded, they can be of any type, so long as they are involved in research and innovation activities. This includes researchers, administrative staff, managerial and technical staff. The definition of what constitutes a staff member takes on board the national law and internal practices of the concerned organizations. One important aspect to consider is the need for the seconding organization to have the necessary legal means in place to allow them to control the supervision and instructions given to the seconded staff member. If needed, and not covered by the existing legal link between the secondee and the sending organization, an additional agreement covering this supervision aspect can be put in place ahead of the secondment. Concerning the researchers seconded during the duration of the project, they can either be doctoral candidates or postdoctoral researchers. In very exceptional circumstances, master's students might be seconded if considered experienced enough to perform the relevant research and innovation tasks and having in place an adequate legal link with a seconding organization. This should always be discussed with the project officer in REA ahead of implementation and decided on a case-by-case basis. The staff members going on secondment must have been actively engaged in research and innovation activities for at least 1 month at the sending institution prior to the first secondment. Last but not least, during the secondment, the staff needs to be devoted full time to the action, and the secondment period can vary between a minimum of 1 to a maximum of 12 months per staff member. The secondments can be split between different institutions. After the period of secondment, the seconded staff should return to their sending institution to maximize the impact of the exchange and ensure transfer of knowledge and long-term collaboration.
A couple of words about what does the action cover in terms of funding. The funding in staff exchanges is based on what we call unit cost, which is equivalent of 1 month spent on secondment by a researcher or another staff member. As you can see on this slide, the unit cost is a bit higher now than in previous calls. It amounts in total to 5,010 euro per month, of which 2,710 euro is what is called category A, and this cost is meant to cover the expenses related to staff member, travel, accommodation, and subsistence during this secondment. This is category A cost. It is not flexible, and it should be fully paid to the staff member seconded. Another part, which is called category B cost, is covering part of research training and any kind of other networking cost related to the project implementation. And the last category is purely management cost, which is 1,000 euro. The category B course is a bit, let's say, flexible, meaning that it, as I said already, it can cover any kind of research training or networking course related to project, or if needed, and depending on each project situation, the category B can be also used to top up the category A allowance if needed, if it is not necessary to cover the full cost of secondment.
Secondments that are eligible for a staff exchanges action when the concern preference is for those secondments to take place between institutions belonging to different sectors of activity, academic to non-academic and vice versa. When the two organizations concerned belong to the same sector of it is very important to remember that in terms of types of exchanges action, when the concerned countries are all EU member states or associated countries, the preference is for those secondments to take place between institutions belonging to different sectors of activity, academic to non-academic and vice versa. When the two organizations concerned belong to the same sector of activity, for example, the academic sector, as is shown in the slide, the secondments should be interdisciplinary in nature, and their total number cannot surpass 1/3 of the total number of secondments for the project. Interdisciplinary secondments integrate aspects from two or more different scientific disciplines. Importantly, those different disciplines are defined according to scientific panels and first-level MSCA keywords, which can be found in the online forms used for the application process. In what concerns secondments taking place between organizations based in EU member states or associated countries and associated partners based in third countries, they are not only allowed, but in addition, in some instances, those staff seconded by the third country organizations themselves are also eligible for funding. Some third countries are identified by the European Commission as high-income third countries, whereas others are identified as low to middle-income third countries. As you can deduct from this slide, when staff is seconded by low to middle-income third countries, those secondments can be funded by the EU, alongside secondments from the EU member states or associated countries. The payment of the respective unit costs is done through the beneficiaries hosting the secondees. As a reminder, secondments between third countries are not eligible, as is the case of secondments between organizations based in one same country. As an example, during the implementation of Project Proceeds, several scientific activities were carried out, including those associated with the following three secondments. A researcher from the University of Sheffield in the UK completed a 3-month stay in INTA in Argentina to analyze relevant policies and actors in the circular economy. Another University of Sheffield researcher spent 6 months on Solagri in Italy to review circular economy practices in the agri-food chain. And finally, a researcher from SEERC in Greece took a 3-month stay in SREM in Serbia to analyze barriers and opportunities in the implementation of the circular economy. These exchanges enabled assessment methods to be applied to real cases and transferred knowledge between institutions of different sectors on the transition to circular supply chains. What benefits, then, for both staff members and organizations coming from participating in a staff exchanges project? In what concerns staff members, they'll acquire enhanced research and transferable skills and competencies, leading to improved employability and career prospects within and outside academia. They will also see their knowledge and innovative ideas converted into products, processes, and services, and they'll have an expanded international exposure, leading to extended networks and opportunities. For the organizations, participating in a staff exchanges project offers innovative ways of cooperation and transfer of knowledge between sectors and disciplines, and it will boost the research and innovation capacity of the participating organizations, giving them availability of human resources with highly qualified researchers, including experts in the fields that may not be familiar to the organizations. Overall, it will lead to strengthened and broader international, interdisciplinary, and intersectoral collaborative networks.
To final with this promotional presentation, as I said, the call is open now. It is closing in October, not very soon, and the budget is a bit higher than the previous one, 97.71 million. That's it for this presentation, and I hope you will be interested and we will see your applications for before the 8th of October. Thank you very much.
I don't know if they have any questions.
Do you have any questions?
So if the audience has no questions, we can proceed with the next presentation from Dr. Athos Agapiou, who is going to present how Earth observation applications help on cultural heritage monitoring.
Good morning, good afternoon to everyone. I hope you can hear me, you can see my screen.
Yes, everything is okay.
Okay, so first of all, many thanks to the organizers of this event and also to Miladen for organizing and the MDPI in general for bringing us this opportunity to share, of what we are doing into the wider community. So I will briefly trying to introduce to what we have been carried out in the last years in the domains of Earth observation, satellite remote sensing for cultural heritage. This is an outline of this presentation. First, a really short introduction, and then what is happening in terms of scientific publications in this specific domain, and then we will go into the core of the presentation, talking about applications, mainly distinguished between site detections and monitoring. Then I will do a very briefly overview of talking also about ground sensors, because there is not only satellite there, and finally with some conclusions, discussions. So, and in terminology for those who are not familiar, I don't think that this is the case, but when we say Earth observation or remote sensing in general, we refer to the science of collecting data from a remote distance. And this is usually done by different types of sensors. Either these are in space, satellites, airborne, or even ground remote sensing platform. So once we have this data, these are then collected and then further processed and interpreted and analyzed. So this gives us the opportunity to monitor and detect changes and everything we want on the surface. And so we live in an area, so we live in a situation where we have a lot of data. So this is something just I wanted to bring this out. So it's not like in the past couple of decades there we are looking of data. So we live in an era where we have a lot of data there. So this is like the concept of digital Earth as well. So there is a struggle there. How can we process all this amount of data, and not only to process them, but also making sense of it. So getting information from the data. And this is where AI and all of this stuff is coming in is coming. And we are working in that direction as well. When we refer to Earth observation for cultural heritage or remote sensing archaeology, this is terminology that has been defined in the past. Most people that are not familiar, they think that this is a recent topic, that this is a new topic. This is not true. Actually, archaeology and cultural heritage were actually one of the first disciplines that have been embraced and have engaged with remote sensing platforms, at the beginning with balloons and then with airplanes and then afterwards in the 60s with satellite imageries and so on. So there is a lot of literature going on there, and the issue that we have not only about cultural heritage applications, but also in other scientific fields is that nowadays we have a different range of sensors that can provide different types of data sets. So there is a need of what is the best way to optimize all this procedure to get the optimum result, as we can say. How we can combine satellite with airborne, with drone, and even ground, sensors to have a better idea of what is happening, especially for cultural heritage sites. So, as I said before, this is a new topic. So this is a paper that has been carried out last 10 years, more or less. So there was an increased scientific interest, if I can say, from researchers and academics working in this field. So that has been a wide application of how satellite can be used for protection and preservation of cultural heritage sites. And in a recent update of that work, you can see here that these are results that have been generated through the Scopus engine, and there is an increased interest. So you see this increase of publications that are coming specifically for remote sensing and, if we could say, geoinformatics. The difficult part that we still have is that these publications can be found in different scientific domains. So it's not only archaeologists that are working in this domain, not only cultural heritage experts, and not only satellite, ICT. So there is a range of disciplines that are coming together and working together, so that you can find these publications in a range of scientific disciplines. And this is like the scientific landscapes based on the Scopus outcomes of what is happening in the terms of Earth observation and cultural heritage remote sensing. So we have image analysis, LiDAR, and several other issues, specific topics, scientific fields that are of interest of specific scientific groups. And of course, there is a trend of things are changing, the interest is moving. So that if you see in the bottom line there of this trend, you see that the focus of this period, more or less, as you can imagine, is AI, and specifically of how we can use deep learning and machine learning methods, especially of how we can utilize big data, a lot of satellite images, through smart ways of getting information based on these techniques. So regarding the applications of how we use satellite images, we can define them into two main categories. The first one is how we use satellite images to detect archaeological sites that are still hidden below the surface. This is site detection, and then we use satellite imageries for monitoring purposes of course, archaeological sites. So we can use satellite images to detect the so-called archaeological proxies. So these are some vegetation anomalies, more or less, but these can be also soil anomalies and several other things. The most famous is vegetation anomalies, known as crop marks in the literature, that we can define, so we can see some vegetation anomalies that might be linked with buried archaeological remains. So below the surface are some archaeological remains, so we can have a first picture, a first view of what is happening below the surface, based, of course, blended with the archaeological context. And for this reason, we use not only high resolution satellite images, so we don't use only the best of the satellite sensors. We often have to use archive data, and we use also open and freely available data coming from Copernicus, from the European Space Agency, coming from NASA, and so on. So this here you see an example from this probably was the first application coming from Landsat 9, exploring Bronze Age earthwork in Europe. And here you can see a really nice example of what is the benefit of using remote sensing, especially working in the near infrared part of the spectrum. On top of your left, on top of left, you can see a really high resolution image here. But when you do some filtering and vegetation anomalies image processing, you can see that there is a rectangular shape which is clear visible there, which is potentially can be linked with a Roman camp. And there are other things that can be done with several others, other processing techniques. Of course, there are limitations, and this is what we are working now in this direction. There is a limitation in terms of how we can establish physically based models, not only image pixel-based evaluations. So we are working in this direction. I don't want to go into that detail. I just wanted to bring this. This is probably something that can pop up in the next few years, but we're trying to establish physically based models working with radiative transfer models. You're working with the ProSail and trying to connect the physical properties of crops with the detection of buried archaeological remains. So for this reason, we have used the ProSail radiative transfer model and trying to also generate synthetic signatures, spectral signatures. So we have established, probably this is the first spectral tube, if I can say, for crop marks for archaeological, that can be used for archaeological proxies, and with a high precision and high accuracy. You can see here all the numbers. So the other direction of how Earth observation can be used for cultural heritage is about site monitoring. So we can use satellite images, we can go back in time, and we can do like a classification and see where urban areas have been. So we can do a multi-temporal map. Here you can see an example coming from the Paphos district. So we can have a statistically reliable outcome of where urban areas are. So we can see the trend, and we can see if archaeological sites have been affected for a long time period, for 30, 40, and even 50 years ago. What we have seen, and this is not only in Cyprus, but we have seen this coming in other regions in the world, we have seen a dramatic increase of urban areas coming closer to archaeological sites, more than 300% in the specific example. Also using not only optical, but also radar data, trying to see with differences in the backscattering. You see here with the rectangles, high differences in the backscattering signal coming from Sentinel-1 sensor for 5 years period. We can also use a pair of Sentinel images, radar images, to detect signal anomalies in a very short time of period, every 5 days. So this is an example we have done after the Beirut explosion. So you can prepare a damage proxy map for covering an extensive area. Also extracting information about the surface temperature, especially this is critical when we talk about energy efficiency of traditional historical buildings. So if you have a historical cluster or where we have historical buildings, you can use also satellite images to get a better understanding of what has been happening in the last 50, 40 years ago. So this is crucial, since it's not easy to locate a sensor in each individual building, traditional building, to record the temperature. Other activities, of course, can be of monitoring archaeological sites regarding looting activity. Here you see an example from the UNESCO archaeological site in Apamea in Syria. Due to the ISIS conflict here and there, you can see the differences using the high resolutions on top and below what has been changed. And this can be documented and mapped, and the statistics can be generated. Just to highlight here that, of course, we understand that satellite cannot stop illicit trafficking. This is not the issue, but at least we can increase the awareness, and at least we can increase the awareness to the people that you are being, this site is being monitored, is being protected. So this is something that really can support this general directive for protecting archaeological sites. Regarding displacement, earthquakes, events, and so on, there has been a lot of interest in this direction. So it's quite easy nowadays to get relative displacements, even absolutely in some time. So you can have horizontal and vertical displacements after an earthquake event. How this can be used? So this can be eventually used blended with civil engineering, and this is an old example that have been carried out and also working in this direction nowadays, trying to get this information into filling element models built by civil engineers, trying to understand how this displacement can have a real impact to archaeological sites. So this is another way of how we can use Earth observation. And before closing the presentation, just I wanted to bring to your attention that usually when we refer to Earth observation, most people refer to satellite. It's not only satellite sensors, we also have ground segments, we also have airborne and other kind of things. And this is a project that we are actually running. Some of the speakers are already here working in this project. So of course, drones equipped with hyperspectral, multispectral, and all these types of cameras are really essential. This is an essential for satellite observation because we need this type of information trying to calibrate and trying to verify the results. And of course, in another direction is how we can use all this information and trying to move beyond our individual discipline. In our field, this is geoinformatics, and how we can bring people coming from the cultural heritage professionals, but of course, archaeologists and also civil engineers and architects, how we can collaborate so we can get the better understanding. Here you can see an example of a documentation coming from the team of one of the next speakers, Dimitrios Karlatos. You see that we can do a documentation. Of course, you do a 3D modeling, and then this can be moved to do several other things. So all these are really crucial. Also GPR, geophysical prospections, and so on. And satellite remote sensing can be blended with other disciplines, especially with Internet of Things. So this is another project that we are collaborating in. So we try to use a multi-scale approach where we have satellites and then we have ground sensors that are established into actual case studies. So we try to do this combination and trying to extract information about hazards and do a predictive modeling if able. So this is a running project as well. So coming to a conclusion, so we know that we have seen the examples of how cultural heritage, how Earth observation and satellite images can be used with cultural heritage, but it's not an easy task. This is something I have to bring into your attention. There are gaps. So this has been already documented in previous reports coming also from European level. But the most important thing is that we need to bring communities together to work. So it's not only about academic or research coming products. We have to bring the ICT and the space community and the academics more or less talking there, also blended with the actual needs of the end users. So the actual end users can be policymakers, can be governmental departments, can be the actual end users that would like to use these technologies, try to embrace these technologies into their everyday life. So this is something that is not still something operable, but this is something that we are working in general as a scientific community. So I hope I was in time, and thank you for listening. Thank you.
Thank you, Dr. Agapiou, for your presentation. I think now that we can pass to the next presenter, which is Dr. Nikos Papadopoulos. He will present us how geophysical prospection methods are used for mapping the cultural dynamics of coastal and shallow aquatic environments.
Okay. Apostle, thank you very much for organizing this under the framework of the project. Also the MDPI, that is a co-organizer, and giving us the floor to this very interesting workshop with quite, I think, interesting talks. Even we heard Athos with these examples from remote sensing. So from my side, I will try just to give a glimpse about how the geophysical prospection methods they can be used to map the cultural dynamics in coastal and shallow aquatic environments. Before I start, I would like to give a small idea about what is geophysics. Geophysics is a word that is coming from the Greek word "gea", which means earth, and physics, and it's actually the science that tries to use the laws of physics in order to determine the physical properties of the interior of the Earth, as it is taken by from the Handbook of Applied Geophysics of Telford and Gerard. So the idea is how to extract quantitative information about the Earth subsurface and the different processes that occur inside the Earth. And actually, what we're trying to do, what we're measuring, we're trying to measure different physical properties coming from, for example, soil resistivity or soil conductivity, the velocity of the seismic waves, the magnetic properties, meaning the magnetic susceptibility and the magnetism of the rocks, the density properties, and all this that they are related with a different signal coming from different geophysical methods. And what it is important to understand in the geophysical methods is the definition of what we so-called anomaly. So if we have a very simple Earth, that it is completely homogeneous, and if we make any kind of measurements, physical measurements of the subsurface, and there is nothing inside the Earth, then we're going to see that the field is completely plain, completely normal, and there is no disturbance in the measurements that we take. However, when there is something hidden, concealed inside the Earth, then if we take any kind of measurements, any kind of different with different sensors, geophysical sensors, then the instruments that they are quite sensitive to different kind of properties, they're going to sense this as the so-called anomaly of the field that we're measuring. So this is quite important to understand that what we're trying to do with the geophysical methods is to see the difference of what we're looking for with respect to the background. Now, when it comes to geophysics, the scale is important. So we have the global geophysics that it is deal with the interior of the Earth, but in a sense of how, for example, the earthquakes are generated, or the tectonics of the Earth, and also how the magnetic and the gravity field of the Earth is generated. When we have a smaller scale, we have the so-called applied geophysics, that it has been used to address problems related to the hydrogeology, to find, for example, aquifers that they're used in order to pump water from the surface, or to address geological problems, geotechnical problems, or even geomorphological ones. And of course, geophysics, it's one of the methods that they have been used since 60s, mostly since the 1960s, in archaeological prospection. And why we would like to apply this method in archaeological research? Because from one side, excavation is extremely expensive. It has large human resources, and it is time consuming, and of course it is distracting. On the other hand, geophysical methods, they need less human resources. They can give a fast and efficient way of mapping the subsurface in a non-destructive way, and it can give a first overview of an archaeological site about to address specific questions, archaeological questions, of course. The thing is that we have to keep in mind that geophysical methods, it's not a panacea, it's not like it's going to solve all the problems of the archaeological research. So this is a vice versa communication with the archaeological teams in order to plan and execute the most effective geophysical survey that it will eventually help the archaeological teams, the archaeological FORH, and generally the cultural heritage community on how to deal and how to deal with and how to proceed with the planning of an archaeological project or a general cultural heritage project. And now, more or less what we're trying to do, as I said, we're trying to take some measurements that they are dealing with physical quantities of the subsurface using a specific instrumentation. Based on this data, there is a workflow to enhance the signal in order to minimize the error, to have a better discrimination between what we're looking for, which is the archaeological relics with respect to the background noise. Also to create some models in order to validate and enhance what we're taking from the measurements. Create visualization maps that are showing actually the physical property of the subsurface in the horizontal scale and the vertical scale, or a combination of this in order to have a 3D representation of these physical properties. And then try to address questions like where to excavate, what type of site we're surveying, or how deep we want to excavate in order to create like typological, spatial and temporal databases that they can be used in order to have a more holistic overview and management of an archaeological site. Now, I would like to focus mostly because as the project is related to coastlines, and what was the idea behind this employment of geophysical methods in coastal site. It comes from this map that it's coming from the Eurostat, that shows that almost half of the population in the EU lives in an area, in coastal areas, that they are about 50 kilometers away from the coast. And if we also make it even more narrow, we can see that almost 50% of the EU population lives in a radius of about 500 meters from the coast. So this we understand that this creates great pressures to cultural sites that because of this population, the activities, the social activities, the economic activities, that they are concentrated in this coastal zone. And for the sake of the presentation, just to also define what we mean coastal zone in our case, it is actually the area that expands from the coast and up to about 20-30 meters from the coast, meaning more or less in the most cases that we have a depth of no more than 4 or 5 meters water depth. This is just to have an idea of the archaeological sites that exist in Greece, and this is actually a photo that is coming from the Greek archaeological cadastre, and that they have been mapped, the declared archaeological sites and monuments in Greece. And just to understand the density only in Crete, we see that almost 70 to 80% of the archaeological sites, they are spanning around the coastline of Crete, which is something similar also for the entire area of Greece. So under this framework, over the last decade, our institute and our foundation has invested a lot of research effort to employ these different techniques, the geophysical techniques, in a number of sites in Crete, in central Greece, but also in Cyprus and in Italy, trying to address specific questions related to the coastal archaeological sites and how these different methods they can be employed, and see the limitations and also the possibilities of these methods. And as I usually say, it is important to know what are the limitations of these methods and what they can give us, and what they cannot give us, because we cannot always try to be optimistic about geophysics going to solve all our problems. But it's a way to see that this kind of methods, they can give a step forward or an extra layer of information in the archaeological community. So I'm just going to give some examples of the different methods that they have been used, starting from ground penetrating radar. Ground penetrating radar is a method that utilizes two antennas, one receiving sensor and one sending, one receiving sensor. The sensing sensor sends an electromagnetic pulse of a specific frequency into the ground, and what we record is the the reflections of this wave based on the different material. So this is a typical B scan, a 2D scan showing the horizontal and the vertical distance along a transect. And I have highlighted two specific hyperbolic reflections that they are caused from point sources, meaning like walls, that they create this specific hyperbolic reflections. And then when we combine different 2D scans in a 3D space, then we can compile depth slices that they're related to different depths. This is an example from the coastal archaeological site of Palekastro in eastern Crete, where with the gray tones, the black tones, we denote areas that they're showing walls and structures along the coast and in the parking place next to the coast, showing actually small buildings and small walls that we can also see the continuation of these walls inside the water. And the challenge in this case is that this specific method, since it is related with the propagation of electromagnetic waves into the ground, the electromagnetic waves have a high degree of attenuation in very saline environment. So it was actually a challenge to see whether this kind of method can be used very next to the coast, as you can see in the images of the operators that they are pushing this cart exactly next to the waves. So it was very surprising also to us that we cannot exclude specific methods only based on the theory, but we should apply this kind of techniques and see whether they're working in a case-by-case scenario. Of course, there are also other cases that we have applied this method and we had almost nothing about the information about the subsurface. The second method that it has been applied is the multi-sensor magnetic gradiometry approach, where, as you can see in this sketch that it has been generated with ChatGPT, we have a cart that it pushes a number of sensors that they are arranged in a row, and all this approach integrated with the GPS and the PC. The measurements are recorded automatically in the ground, and this gives us the flexibility to cover larger areas in a smaller period of time. This is an example coming from the area of Poros in Eluda in eastern Crete, and just to have an idea of the details that we can have from this kind of maps, that they record the variability of the magnetic properties of the subsurface. This is the part from the southern part of the site where we can see buildings, walls and buildings, and that they are below the earth of about 30 to 70 centimeters. And then if we also use this approach also into the water, how we can outline the building complex with internal division. And of course, even in a more harsh environment, like a rocky environment, in this case, rocky coastline, again with quite good results about the mapping of the submerged archaeological structures, that they are now below the sea floor and they are not visible to the naked eye. Moving further to the electrical resistivity tomography method, it's actually a method that utilizes a number of electrodes that they are connected with a multi-clone cables, and trying to record the variation of the resistivity properties of the subsurface. Specific challenges they had to address in such approach, because resistivity method, since it measures the resistivity of the subsurface and utilize electrical current that goes into the earth, it can be affected by the saline water. So there was a great effort to see the effectiveness of this method based on synthetic modeling that it has been done in the lab, trying to see what is the effect of the depth of the water if we underestimate the resistivity of the water into the processing procedure, and also what is the variation or the resolving capabilities, the horizontal and the vertical resolving capabilities of this method. And then trying to see in the real situation, like in the first slide that we see here, and that they have been outlined resistive structures that they belong to walls, that they are below the seawater, below the seabed, or to see the stratigraphy of the surface and see how we can map the bedrock and how this is related, for example, with the construction of shipsets in the archaeological site, or just to see in the archaeological site how it is affected by the tectonic movement, as in the case of Delos, where we can see the two big faults that they have caused the subsidence of the bedrock in this archaeological site. Of course, the same challenges they stand for the 3D case, where again, based on synthetic modeling, we have tried to see whether how this can be exploited, the method can be exploited in order to create maps, horizontal maps in different depth layers. And the application in a real example, where we can see on the right side the slices, the depth slices at the different depths going from 40 centimeters to 1 meter, 1.5 meter, and how this method can map us the variation of the continuation, the plan view of a structure, of a building structure, and also to have a sense of the thickness of this structure below the seabed. And of course, if we want to make a survey that it is even faster, all this approach can be integrated in a small boat. The instrumentation, the resistive instrumentation to be integrated with the GPS, and then try to cover a larger area, like with moving the boat, the small boat, in parallel transects. Here we can see the transects on the bottom left, the transects that have been carried out in the archaeological site of Pholos, with an effort to map the continuation of the fortress wall of the city, and also individual structures. On the top bottom, we can see the different depth slices at different depths, and on the bottom right, the interpretation showing the continuation of the fortress wall of the city, that it is now submerged in the water of about 2 meters below the sea. And what we can see here with the resistivity, high resistivity feature, how it continues the fortress wall in a depth of about 1.5 meters below the seabed. And in even more experimental approach, how this method can be also used to map the outline of metallic shipwrecks. So this is an example with a collaboration that we had with University of Adelaide, and the different depth slices here outlining with blue colors as a conductive target the outline of the metallic shipwreck going from about 50 centimeters to about 2.5 meters below the river, and how this data afterwards they can be combined in order to create three-dimensional models of the specific shipwreck. Lately, we have also tried to use also other approaches like electromagnetic induction approach in order to map the very shallow part of the area. Electromagnetic induction approaches, it's like they have the same principle as the ground penetrating radar, where the signal, the electromagnetic signal, has high attenuation in saline environments. Thus, that was extremely challenging for us to see whether this kind of method can be used in a very shallow part in water environments, to see if we can map archaeological structures. So, based on the collaboration we had with the University of Potsdam, and under the framework of a PhD project that it is running, there is an effort to model different kind of instruments to see whether this kind of instruments they can be used to sense, to have a resolving capabilities of structures based on synthetic modeling with different, as I said, instrumentation, different configurations, different processing approach, Based on these preliminary results, the synthetic modeling, they were quite encouraging, and we had the first survey in the archaeological site of Stomio, where a visible Roman villa exists, in order to test the different kind of instrumentation on top of known structures to validate this kind of approach. And we can see the different kind results with different kind of instrumentations, where we can see the outline of the Roman villa, giving a very good indication that this approach can have further potential in mapping of coastal archaeological sites. And the experimentation also continues with also seismic methods. Seismic method is a very well-known method because it is used. It has been used originally used in oil industry, but it has also many other applications for geotechnical applications. So this is one of the first approach to use this kind of method to map shallow submerged archaeological sites, again with synthetic modeling based on the collaboration we had with the Technical University of Crete, and in situ verification of this kind of method with real data. Now, of course, what is important in the coastal archaeological sites, and as is the integration of the different this approach, the different geophysical approaches, the different geophysical methods, along with other methods and techniques that they have been incorporated also in the coastline project. And based on this, we had the chance during 2016 and 2021 to have a great collaboration with the University of Geneva and the F48 of Underwater Antiquities in Greece, where we had the chance to test different these different geophysical methods, along with drones, sonar survey, shallow underwater photogrammetry, in order giving us the opportunity to have a more holistic and more complete view of the different methods in a single archaeological site. These are some results spanning from the creation of the orthophoto, the sonar bathymetry, the bathymetry compiled from a GPS and the total station, results from the GPR along the coast, magnetic gradiometry results for the very shallow part, resistivity tomography, both the shallow and the deeper part, and so on, and also the underwater photogrammetry. And actually, this is an open lab that gave us a lot of insight about the limitation of each method. And of course, the final goal was to compile map like this one, showing combining what we have found with the classical underwater archaeological survey with in situ survey and mapping, what it was visible, and then complete the picture with the geophysical methods and what it is not visible in the very shallow part and the coastal area, having in this case a more unique and more holistic approach of the site, completing the picture of the Lambayan archaeological site, which is a submerged prehistoric area. There was also an effort to compile some small books that this kind of methods and the preliminary results, they have been indicated in these books. These are freely available through the website, so whoever is interested, I can also send the link to download it. Many thanks to the funding agencies that they made all this work to be to make it feasible, and of course to the team behind, because this is not one-man show. It's many people that they have placed a lot of effort to this direction. And with this one, I would like to thank you for your attention. And I hope I was in time. Thank you very much.
Thank you, Dr. Papadopoulos, for sharing valuable insights on geophysical prospection methods and highlighting the importance of various methods like electrical resistivity, seismic methods, etc., for mapping the cultural dynamics in shallow waters. So we're going to our next presenter, which is Dr. Dimitrios Skarlatos. He is going to present how the water fraction is affecting the coastal optical bathymetry. Dimitri, the floor is yours.
Thank you, Apostolis. Thank you and the organizers for this invitation. I'm afraid I'm going to be not that interesting as the two previous presenters. I'm going to discuss about low-cost technologies and techniques to map what was already found. So I will not be talking about things that we're trying, or cultural heritage that we're trying to find, but rather than cultural heritage that we're trying to measure after it was found. I'm going to be in between those two, satellites and underwater or close to water. Mainly, I'm going to discuss about dead ship drones for mapping the coastal zone. Now, the importance of the coastal zone has been highlighted by the previous presenter, by Dr. Papadopoulos. And of course, it is of interest because of the pollution and litter and marine life and animal forests in this zone. It concentrates a lot of marine activities like construction, mining, marinas, and ports. And you can see here a fine example of sites, archaeological sites that are here. Actually, the whole peninsula is an archaeological area, open. And the new marina in Agia Napa that has been built in this area. And actually, we have been asked to do the aerial mapping along with archaeologists that were doing the underwater mapping of finds in that area. Now, the extent of this marina is, as you can see, quite large, is almost 500 meters in sea. And you are going to see in some following slides, the work we have done there. Now, when we are asked to map this coastal zone, especially the gray zone that Dr. Papadopoulos mentioned, meaning the 0 to 5 meter depth, which is quite critical and quite difficult, we have some options. Each one of those has its advantages and disadvantages. For example, we can use multi-beam or single-beam echo sounder. Very nice machines, quite expensive though, difficult to operate. I mean, you need a boat going up and forth, so it is quite costly. And then again, you don't get any visual content, just a point cloud, let's put it this way, of the bottom, of the sea bottom. We have optical ways on resolving bathymetry, and you can see here the satellite or derived bathymetry or spectral derived bathymetry. And there we can explode satellite images to measure the depth of Puka Lagoon, for this example, in Poland. This technique is quite sensitive. It needs calibration. It's not accurate enough for quite many applications, but it's holistic. It can cover large areas. It's single image, so it is quite easy to acquire satellite images. And in some cases, it's even at zero cost. So it is a quite viable option. Otherwise, you can utilize LiDAR, so manned aerial flights, and unmanned if you have a green LiDAR to cover those areas. Of course, now we are heavily dependent on water visibility. And as you can see from the scan lines, not all of the scan lines were completed, and there are areas where the light could not penetrate. Although that on this area, the deepest water was just 5 meters, 5.3 actually. So you can see that depending on the water visibility, some techniques might not work. LiDAR, for example, LiDAR flights are sometimes able to measure the sea bottom at 25, 30, even 50 meters in some cases. But here, in this particular case, it was unable to reach 5 meters. Or we can use two-media photogrammetry, which is the cheapest of all, using simple drones taking photographs over the water body. Here, the coverage was even worse, as you can see. It's even worse than the LiDAR, better than the multi-beam, because the multi-beam is quite expensive. And you are able to cover most of the area, once again, heavily dependent on visibility. Why do we need to do that? In case we have some archaeological finds or some cultural heritage underwater, then we can easily use divers or submersibles to take photos and have a very nice map, detailed 3D models of the finds or the site. This is not possible when the water is very shallow, so we don't have enough distance for the submersible or the diver to be able to take photos of the sea bottom. Another case scenario is when we need to combine aerial photos, for example, drone images to cover larger areas with underwater photos for details in some parts of this large area that we have mapped with drones. But in my opinion, the most important scenario, the most important case that we need to use drones is when we want to link overground and underwater finds. So we need to correlate areas and map them in a uniform manner, both inland and underwater. That's where this mapping technique, or let's say photogrammetry with using two-media approach, is very, very useful. The obvious problem, the elephant in the room, is the water refraction. And water refractions affects heavily the final results of a geometric method such as photogrammetry. Unfortunately, it is very easy to forget that when you're seeing this kind of photos. And actually, this is the photo of where the marina was built, the marina that I have showed you earlier. This is our survey. And when you see this kind of orthophotos and orthophoto mosaics, it is very easy to forget that you did a mistake. And the mistake there is that you didn't take the proper consideration of water refraction. I must agree totally that the end result is mesmerizing. It's very nice, and it is very easy to forget the problems there. All SFM techniques, or SFM structure from motion and multi-view stereo software, which is easily available to everybody, along with a quite cheap drone of 1,000, 2,000, 3,000 euros, and you are able to get this kind of results. Or this kind of results. For example, there you can see the Lachi port and the ancient breakwater under the new breakwater of the new port. Or even most importantly, you can see where the ancient breakwater was, and actually it was destroyed in order to create the entrance of the new port. And actually you can see here the whole breakwater of the ancient port. So the obvious advantage of photogrammetry using drones is that you have you can combine bathymetry, so sea bottom, and not just sea bottom, but actually to have a visual indication of what is underwater. So this is a unique let's say, ability of photogrammetry. That's why most people, along with the fact that it is very cheap, that's why a lot of people are using coastal aerial photos to produce this kind of orthophoto maps. And we did a lot, as you can see here. We even did a very large area. You can see here the Paphos port, and this is actually 14 kilometers coastal side from manned aerial plane. Now, does it affect? Does the water refraction really affects the final result? Because some people are not even aware that there is the water refraction problem, and they just fly, take the nice orthophotos from automated process such as SFM MVS, and they say we can produce nice orthophoto maps. So we did some simulations, and it is quite easy to reverse the problem. So if you have, let's say, a flat bottom at 1, 2, 3, 4, 15 meters depth, you can estimate the problem that the water refraction does. And we did that for, let's say, an example of a drone flight at 100 meters or 200 meters with a 25-meter equivalent length and with 80% overlap. And this is the result. So what you're actually seeing here is, for the example, let's say, of overlap 80% with a drone flight at 100 meters, you can see in the very last surface down here, the reddish one, that if we were mapping a flat bottom at 15 meters, the error that we will have if we ignored water refraction would be 8 meters, roughly. Okay, maybe 7, because you can see that the surface is not flat anymore. And if you are flying in 200 meters with the same drone, still again, the deformation of the surface that you're mapping, or the, let's say, the error, the average error of the depth is around 7.5 meters, not to mention that the flat bottom, you will, instead of a flat bottom, you will get a curvature area. And of course, a lot of people argue that when I'm flying, let's say, at 1,000 meters or 3,000 meters with a manned airplane, so you have only 10 meters depth and 3,000 meters of air, then we can ignore it. Of course, you cannot ignore it, because even when you're flying with a professional manned mapping Vexel camera, for example, in 1,000 or even 3,000 meters above sea level, then again, you have the same kind of error. So in 50 meters depth, you have already 7 meters of error. So instead of reading the proper 15 meters, you're actually reading only 8 meters with a total different surface instead of a flat one. So we have established that the ratio of flying height to depth does not reduce the water refraction effect. So it doesn't depend how high you fly, you still have to take into consideration that there is water refraction. Can we fix it? Yes, we can. We have developed 2 different methodologies, but I would like to stick on this one because I'm going to use it later on my presentation. One way to correct the problem is make differential corrections to the photos. This is like changing the focal length of the photo. I know it sounds strange, but it is like changing the focal length and using a different focal length for each pixel in the photo depending on the actual depth, which of course you don't know. So this is an approximate solution. But regardless the solution, what I'm trying here to say is that water refraction can be corrected if you use differential focal length. And we have done that. For example, here you can see the original photo and the corrected one. And if I go back and forth, you will be able to understand that what's under the water surface is kind of corrected or differentially corrected, while the part of the photo that it is land and above the seawater doesn't change at all. And what kind of correction do we have? And you can see here on the previous example, the corrected and the uncorrected contours, bathymetric contours. And as you may see in 2 meters, so here, if you don't take water refraction into account and go through the automated techniques, you get a depth of 2 meters. You get the red contour of -2 meters here. But if you take water refraction into consideration, the actual depth here is 3 meters. And this goes on. Of course, here, for example, you may see the correct and rock bathymetric contours of -4 and -6 meters. So approximately roughly 50% error. And of course, here the contour is quite deformed, so it's not exactly the same. So there is a way to correct depth. What about horizontal error? I don't care about depth because all I want to see is what's under the sea bottom. So if it's rock or if it's Posidonia or what else? Still, this depth error is translated into horizontal error in your final orthophotos, which varies, of course, depending on depth. And as you can see, we were able to verify that there is an error of just 0.2 to 0.3 meters when you're dealing with 1.6 meters of depth. But in deeper waters, for example, here, and here is almost 14 meters depth, then this deformation, this horizontal effect is up to 2 meters. So it's not negligible. And also, if you do properly the corrections, the water refraction corrections, the software it is more easy for the software to produce a nice orthophoto. And as you can see here, the details are more pronounced, so even you may have improvement in orthophoto and texturing of the photos. So this is all gain if you do the water refraction. But I would like also to point another issue. So some people might argue that, okay, we don't care about the sea part. We will chop out, we will crop the area of the sea. We will not show it. We will not produce contours there or DSM or whatever. So we are okay. Well, this is partly true because you don't have control points, and usually when we're flying with drones, when we are applying photogrammetry or SFM or whatever, we want to have control points around the area. So this is not possible, of course, when you're dealing with water, but this is kindly partially compensated if you are using RTK drones, which is the norm today. So we are okay. Not really. Actually, when you are flying in such areas, you will have some photos that are completely on land. They're imaging part of land. Some other photos that are imaging partially land and partially water, and some other photos that are on shallow waters or even deeper waters. So when you are actually doing structure from motion, then you are also doing self-calibration of the camera. So you are using all the photos to calculate the focal length of the camera, which is the norm today because this kind of photographic equipment on drones are not very accurate, and you are performing self-calibration as part of structure from motion. But as I mentioned previously, the water refraction can be adjusted if you properly use the focal length, which means that these two things are related. So when you're using self-calibration and SFM, you're actually calculating an average focal length of the whole area, over water and underwater. And by doing so, when you are using this calibrated focal length that you have estimated, this will affect both camera location and the point cloud that you are building, that you are calculating for the land. So basically, what you are doing is infecting, let's put it this way, the land part by the water refraction and the bad estimation of the focal length that you are doing. So after all, the whole block is affected by that. I don't know by how much, because this is quite difficult to estimate, because it depends on the portion of the images of how deep the water it is and so on. So we haven't done any artificial testing over that part, but I am sure that it is considerable for some applications. So takeaway messages, and I hope that I am on time. Photogrammetry and SFM and MVS as it is applied nowadays, it is affected when you are flying above water, and you should know that. Now, everybody knows that. The water refraction affects a lot depth estimation, regardless of the flying height. So it doesn't matter if you fly 1,000 meters and you have 1 meter of water, you are still have a depth estimation error, which is roughly half a meter, even for 1 meter of depth. It also affects horizontal accuracy. So if you are only using the orthophotos to take some horizontal measurements, you are also affected. But the amazing thing is that if you have blocks above land and sea, then the whole block is affected, and actually even the measurements in land are not correct. So this may come as a surprise, but this is it. So you may choose to ignore water refraction and make no corrections and use the photos as you took them and make all the SFM MVS process and get very nice DSM and orthophotos. And you might be able to do that if the application that the orthophotos and the DSM is aiming to doesn't care about this kind of accuracy. So you may choose to ignore it, but at least this must be an educated decision, and you must be aware of the errors that you are producing, and you might choose to ignore them if the application doesn't really care about the magnitude of those errors. So this is it. Thank you for your attention. If you want or if you wish to learn more, please consider following the third edition of the 3D underwater mapping. And this year will be done in Vienna and will be hosted by Professor Gottfried Maldenberger. Thank you very much.
We would like to thank Dr. Skarlatos for the inspiring presentation regarding the coastal bathymetry and how the water refraction is affecting orthomosaics on the coastal zone. So with this, we have finished the first session, and we have a few minutes for Q&A. As I can see, we have 3 questions for Nikos Papadopoulos. So Nico, I don't know, you can answer those questions. You can hear us. And we have also one question for Dimitris Karlatos. So that is for Emiliano Zampetti. Thank you for your in-depth presentation, Dr. Karlatos. I have a question about the cost analysis of drone applications in relation to drone flight duration, and therefore the adoption of many drones to collect data over a large area or a large number of flights. Dimitri, you are muted, so we cannot hear you.
Yes, thank you for the question. I will try to interpret it a little bit because it's not quite clear for me. Drone flight duration and how this affects the end result. Well, flight duration, because we did one with Apostolis quite recently, matters. For example, in order to avoid sun glitter, you need to fly quite early. And the higher the sun goes, then you're starting having sun glitter on the sea waves, on the side of the sea waves. And later on, you may get even the very ugly hotspot from the sun itself. So you need to go quite early when the sun is low. That means that you have a window, flight window of roughly 1.5 hours, depending on the fee of the area of the that you are in Earth. So you have, let's say, 1 or 1.5 hour window. Can you cover the area you want? Probably not. But you can use, as you already suggested, a larger number of drones to cover parts of the area, or you may use some drones that are capable of swarm flights. I don't want to give the name of the company now, but there is this kind of you are able to have a central station that controls 1, 2, 3, 4, 5, up to 12 drones that will be covering the same area or the same area of interest at the same time, with drones flying at different places. Cost analysis between drone and other techniques. Well, it is definitely much cheaper. The cost of a drone is like maybe 2,000–3,000 euros. The cost of a LiDAR drone with green LiDAR for penetration, it starts from 100,000 euros and going up. So the cost in terms of equipment is huge. And I'm not talking about monthly LiDAR. I'm not talking about multi-beam, because multi-beam doesn't. Anyway, LiDAR and multi-beam do not give you a visual effect. So you basically end up with a lot of points and a very nice depth, but you cannot see what is there. The other option is satellite-derived bathymetry, which is even cheaper. So basically, you can do it for nothing. But there, you have a very big pixel size, maybe 6 meters, because the photo that I have shown you. And actually, you may read. There are open data there. Actually, that was published. I'm sorry, MDPI in Nature Scientific Data with open access. But there, the problem is that you don't get the image of the sea bottom. You may get the whole area if you are lucky with the satellite photos, but this is doable. And still, you need to have some kind of training data to resolve the depth from spectral derived bathymetry. So you need to have some kind of information about depth. And this is a little bit tricky process. So yes, satellite bathymetry is definitely the cheaper one, but with very coarse pixel size. And generally speaking, drones and photogrammetry are preferred because you get to see the results, very nice results indeed, attractive results, very fast. Thank you.
for answering the questions of Emiliano. I think, Nikos, you have more than 3 questions, so as we are running out of time and we need to go to a short break, I think that you can answer 2 questions from the questions that they asked to you. As I can see, you have already answered to the chat, but just for informing all our participants, yeah, you can choose what questions you can answer.
Okay, thank you, Emiliano and Dora, for the nice questions. I have written in the chat basic answers, but if they need or anybody else needs some extra information, I can also send publications related to the results that they have been shown, that they show more details about these questions. Okay, I don't want to take more of your time.
Our webinar next presenter is Dr. Alessandra Capolupo. So she will present us the workflows from geoinformatics, how we can combine multi-source data in cultural heritage. So Alessandra, the floor is yours.
Thank you. Good morning, everyone, or good afternoon, according where you are. So, as Apostolos mentioned, now I'm going to tell you something about a viable geomatic workflow that you can apply to integrate the information provided by multi-source data input in order to reconstruct a three-dimensional representation of a cultural site. Why that? Actually, that's a 3D digital representation is really important. We are giving a lot of attention to the digital twin currently, even if it was recognized as a powerful tool just some years ago, and it was listed in UNESCO World Heritage List in 1985, just because it allows us to describe actually the health status of a cultural heritage site, and so it allows us to monitor their health status, and so to detect the optimal strategy to monitor and to preserve them. Of course, in order to meet such a goal, over the years, several techniques have been developed, but here I just mentioned the most common ones. Even if define which is the optimal one, which is the best one, is actually possible, because the choice of the technology depends on several factors, such as, for example, the complexity and the size of the area under investigation, as well as the level of accuracy that you want to achieve. So the 3 main techniques that actually are to date being involved are the application of drones and the application of terrestrial laser scanners. Although these 2 methods cannot be applied alone, but they need the ground control points collected by the application of a topographic survey usually performed by using a global navigation satellite system. However, decide which one is more useful is very difficult, because all these techniques are not limitation-free. For example, terrestrial laser scanning is really good because it allows to extract 3D dense point clouds of a specific sites in a very quickly. However, it has a lot of disadvantages, for example, mainly linked with the cost of the instrument, as well as the difficulties to survey some areas that are difficult to reach, or also because also linked with the position inclination of the instrument. For example, if you want to generate a higher accurate dense point clouds, you should get this instrument close to the area that you want to survey, and also the inclination of the instrument should be perfectly perpendicular with the sites that you are going to survey. So for that reason, now recently, it was a little bit less used, and actually the drones gain the floor, specifically when the extraction from motion techniques is paired with the multi-view stereo techniques. This is a very flexible tool because it allows to define the survey according to the user needs, both in terms of temporal resolution and also geometric resolution, because we can drastically reduce the flight quotas according to the size of the object under investigation without any kind of issues for the pilot. And at the same time, also the cost of this instrument is not so high. Actually, in the last few years, its price decreases a lot. But also these techniques actually has some disadvantages, mainly due to the accuracy of the generated dense point cloud, because usually the density and the homogeneity of the point clouds is lower than that one derived by terrestrial laser scanner. And also in this case, it's the accuracy of the final outcomes is actually affected by several elements, several factors, specifically, for example, the amount of the ground control point, but also the distribution of the ground control point, as well as the operative pipeline that's usually adopted to use. In addition, we also know that actually the time to collect the data over large areas is not so much, but there is an exception when we had to survey higher wide areas. In this case, the time needed is much higher. So since no one of these techniques is limitation-free, recently we are thinking to merge the information provided by these two approaches and to get into the data fusion techniques. Of course, when we talk about data fusion techniques, we should distinguish three different levels of fusion: low, medium, high. We talk about low level when the fusion is obtained at raw data level and the outcome is a raw data output. At the same time, we talk about medium level when the fusion is made with at the level of the raw data, but the outcome is related to the features. We talk instead about a high level of integration when we apply some specific fuzzy logic methods or statistical methods to perform that data fusion. So for that reason, actually, what we want to do now, we want to actually show a potential, a viable workflow that can effectively support the 3D reconstruction of a cultural heritage. And specifically, we are going to show the experiment that was carried out on the Old Saint Monastery of Cuti in Puglia. This pilot site was selected just because it is one of the few examples of well-conceived of Apulian Romanesque architecture in Puglia region. So it's really relevant from the archaeological point of view. And here you can see that the operative workflow is mainly broken down in 6 main primary steps. So first of all, we should start performing the field data campaigns. And in our case, 3 different campaigns were carried out. The former was aimed at gathering and collecting the data and the photogrammetric pictures by adopting a drone. In our case, we just used a DJI Inspire 1 equipped with a consumer camera. And we collected a total of 202 images. Instead, simultaneously, also a terrestrial scanner survey was conducted by using a Leica RTC 360 3D laser scanner, and a total of 34 scans were gathered. However, we didn't use all of them, but just 24, because the remaining 10 scans were actually referred to the internal part of the monastery. And so for that reason, they were not involved in the scope of this experiment. Simultaneously to these 2 surveys, also a topographic survey was conducted, and so 21 permanent natural elements was was gathered, and these points were subsequently split into different categories. The former, characterized by the amount of 11 points, were used as ground control point in order to georeference the scans and the photogrammetric images, and so to improve their geometric accuracy. And the remaining 10 ones were used instead to assess the accuracy of the final outcomes. So after that, the operative workflow started. Of course, the scans and the photogrammetric pictures were analyzed separately. And here you can see just a summary of the pipeline that was adopted to process the photogrammetric data, and specifically 4 main steps were defined. All this pipeline was implemented by using Metashape, that is one of the most common among the commercial software. So we started just setting the workspace and the dataset. We oriented the block of images collected, and after that, we imported the ground control points in order to improve the georeferencing procedures, and also all the parts that were not directly involved in our reconstruction were removed. So the main outcomes of this procedure was a dense point cloud and a 3D text model. Simultaneously, with the same desktop was also performed a terrestrial laser scanner pipeline that was made by using Cyclone software. And also in this case, after setting the workspace and the dataset, we started co-registering the different scans collected. And this co-registration was performed by detecting specific homologous points among the different scans. So georeferencing and filtering states, and after that, the final dense point cloud was generated. When the 2 models were derived, the performance assessment comparison should start in order to assess the information, the accuracy of the 2 models, and it was conducted just considering 2 different steps. The former was based on the comparison of the 2 models in terms of acquisition and processing time, as well as by comparing the number of points and specifically the density of points, so the volume density, and also the divergence, the distance between these 2 derived models. But since we know that that each 3D size structure can be actually well described by using the eigenvalues, we also decided to compute some important features that are relevant to understand and analyzing the health status of a site of heritage. And so for that reason, here you can find a list of the main eigenvalue-based features that was analyzed. However, since we know actually that because of the instruments and also because of the environment conditions, a lot of errors could occur, and this could affect strongly the eigenvalues, we also decided to apply the Gaussian law variance propagation in order to understand how the different features were affected by the errors. And so here you can just see how the equation to gather this information were modified. Subsequently, the application of the Gaussian law equation. Of course, all these steps was performed by developing a specific code in our environment. So after the evaluation of the 2 models, and so the analysis to see if the 2 models were comparable or not, and so if they could be integrated or not, the realignment and co-registration of point clouds phase started. And in this case, since the accuracy obtained with the dense point cloud generated by the terrestrial scanner was much higher than the other one, we decided to use this one as benchmark. And so for that reason, the data fusion procedure started. And so we create a fused model by gathering the information of the both models so that we obtained before, and we started evaluating its accuracy just by considering the uncertainties of the model-to-model distance, of the model-to-model cloud comparison, and the original cloud index that is able to specify where the points of the final outcomes they are extracted from. So here you can just see actually two models of them derived by the application of drones and terrestrial laser scanners. I'm sorry, maybe the connection is not very well, so they seems to be much lower than it was expected. But in this way, you can just have a first qualitative comparison about the two remaining models. You can see that for sure, the number of points of the terrestrial laser count that compose the point clouds derived by the terrestrial laser scan derived clouds is much higher, and so the texture are defined, the details are much finer. However, if you notice, there was a lack of information because a lot of parts of these monasteries was not reconstructed. Specifically, that's one belonging to the roof. To the roof of the monastery. So just considering, just giving some number, we can confirm what we saw from the qualitative analysis of the dense point clouds. Indeed, the number of points of the terrestrial laser scanner clouds is much higher. That's one derived from UAV. But if we analyze the volume density, we can also see more specifically where the lack of information appeared in the point clouds of the terrestrial laser scanner, and that's also the homogeneity of the point clouds is not perfectly equal along the point clouds, and this depends more or less from the distance of the instruments from the monastery, from the different parts of the monastery. However, if we consider just the time that we need to collect and process the data, we can see that terrestrial laser scanner appears as affordable tools because the sum of this time is much lower than that one needed to collect and process the data from photogram matrix one. So it appears that actually terrestrial laser scanner should be the most accurate and also the most affordable because of the number of points and the time needed, but actually if you saw is not really like that, just because we have a lack of information. And so we are able to reconstruct well some parts of the monastery, but not the entire structure of the sites under investigation. Here you can see a more deep investigation of the divergences between these two models, and specifically the model-to-model cloud comparison. And you can see that these parameters, these indicators ranges between -0.5 and 0.5. However, if you go deeply, you can see that the extreme values are obtained because are obtained in the area where the lack of information occurred. So they depend on the vegetation, on the vegetated areas, as well as on the roof of the top. Instead, if we just restrict our investigation to the rest, to the horizontal and vertical face of our monastery, you can see that the range, the divergence is the order of millimeters. And so for that reason, we don't have so much divergences between the two models. And also considering the inaccuracies of the model-to-model cloud comparison, we can actually see that the two models don't show so many divergences. Indeed, the uncertainties of the order just of millimeters. So the two models are very good, and this indicator ensure the comparability and compatibility of these models, and so that ensure that two models that can be integrated. Here you can just see some comparison of the EO&GEO value, but as I said before, actually we didn't limit our research to just compare that. This is just to show how the EO&GEO values work. And if you compare the different values, you can see that the ranges are absolutely the same for all of them. However, the second EO&GEO values shows a different trend, while the first and the third one has the same trend in both models. And here just an example of the main features that were collected. Just for brevity, I decided to not show you all the features that can be that we calculated, but just 2 of them, in order to show that the trends and the regions is perfect and comparable, so that we don't have so many divergences among them. However, instead, I want to show you an interesting results related to the variance that affect the geometric features. If you are considering just the variance of the second and third EO&GEO value, you can see that the trends and the ranges, the values are perfectly equal. Instead, if you consider just the first EO&GEO value, you can see that the true trends are not the same. Indeed, is much higher. The divergences, the differences are much higher at low values. But since these values corresponded to vegetated areas, it means that actually the errors should not affect our investigation, because our scope was just referred to the reconstruction of the pilot sites. So here you can just see the final mode that was obtained by integrating the 2 models. As you can see, we took advantages of the main properties of the both models, so we were able to reconstruct the interior science and also to get all the information provided by the terrestrial laser scanner in order to increase the number of points, and so also the details that are actually described. And in order to see which models affect more the final one, we also computed the original cloud index. As you can see, in violet are reported all the points that are derived from drones. Instead, in red are reported the points derived by terrestrial laser scanner. And of course, all part that was related to a lack of, it was affected by a lack of information were just acquired by drones. Instead, where the points were get read by the lens point cloud of the terrestrial laser scanner, they were actually used to generate the final outcome, so the final models. So what we can say that actually this hybrid model represents maybe the optimal viable solution to optimize the workflow in order to get the most suitable information by the both techniques, and so to reconstruct the entire science and also to increase the accuracy of our final model, and so the quality of our final models. So thank you for your attention. I try to be on time. I hope to be on time.
Sandra, for sharing valuable insights on regarding the geoinformatics workflows and how we can merge data and we can let's say compare the data for various sources. So now it's my turn. I will share my screen. I will present you how we can create visualizations used on by using drone-based data on cultural heritage. But before this, I will shortly present you the importance of geoinformatics. So according to the United Nations Committee of Experts on Global Geospatial Information Management, and their report on future trends in geospatial information management, the 5 to 10 year vision. So they note that the year 2023 is a milestone it will be a milestone in the evolution of the global effort regarding the economic, environment, social dimensions of sustainability. In this vision, the geoinformatics and in general the geospatial information and technologies will play a crucial role in leveraging the potential of the fourth industrial revolution. So the creation of geoinformatics and all derivatives that are producing from this kind of information will empower decision makers with timely, accurate, and trustworthy information, and making them in creating and shaping policies and plans that are that will be influential to our world. More specific, they believe that the rise of autonomous systems has shaped and will continue to shape the increasing need of near real-time information, and they are expecting the next 5 to 10 years to see a very big change in the way that the geospatial information will shape and will be shaped. So in terms of this, a few years ago, I read this, let's say, sentence from Bill Gates, which he mentioned that we always overestimate the change that will occur in the next 2 years and underestimate the change that will occur in the next 10. So here you can see a few photographs from the drones that we used 10 to 11 years ago with very, very small sensors and with limited capabilities. So at this time, as also Alessandra mentioned and Dimitris, we have various sensors, different ones, small sensors that can acquire data in different bands and with a very high resolution, that begin acquire very, very high resolution data, and with this data we can produce geospatial information. So by using the drones, we had the idea of visualizing in 3D the Lesbos Geopark, a place in Lesbos Geopark, by using different scales on this 3D geovisualization, where the visitors can see in high detail all fossiliferous places. So we're trying to leverage UAS data and cartographic illustrations in this virtual reality environment. So the idea is to go to Placas Park and by using our equipment, acquire data in 2 different scales, 2 different spatial scales, and of course cartographic scales, for the creation of a 3D virtual tour that is that is based on the use of cartographic visual aids. And I will continue and I will present you what I mean with cartographic visual aids. So the main objective was to create, as I said before, the immersive experience of a geosite by using and fusing this kind of UAV and terrestrial data. So the combination was in between UAV, very high resolution data, terrestrial images, 360 panoramas, and some maps that were some cartographic products, maps that they were previously created for this scope. We think that we can combine all this kind of information to generate visualization and interactive navigation and an immersive visit in the geosite. So the thing behind all this process was to try to replicate the real in situ visit. A few words about the study area. So the island of Lesbos was recognized as UNESCO Global Geopark in 2015. So it consists more than 100 geosites that covering almost all island, and is the first UNESCO Global Geopark in Greece. So one small part of this geopark is the Placas Park. This small, it's a small portion, let's say, of this geopark, of the Lesbos Geopark, which is located to Sigri on the western part of the island. So this park has 2 sections, the western coast and the eastern inland. Features of 37 excavation sites where fossil and root systems, tree trunks that are preserved in their original growth orientation and place can be visited by the visitors of this park. So it has a unique combination of coastal and inland petrified formation. So that is let's say great. Great for a case study area regarding the visualization of these fossiliferous systems. So we decided that our methodology will follow, of course, 3 pillars. The first pillar is the data acquisition, second, the data processing, and the data geovisualization in 2 different scales, 2 different cartographic scales. That means we have different resolution on the data that we collected. And in terms of the equipment, we used various sensors, terrestrial and airborne sensors, as you can see here, and we tested all the 3D visualization that we created with a VR headset in order to let's say see how we can create the most effective visualization regarding the visit of the site. So the data acquisition was of course realized by using drones. We collected almost 1,000 images with one flight with a resolution of 0.5 centimeters, and we collected also more than 500 terrestrial photos from 15 different geosites on fossiliferous sites on the park, having a resolution of 0.1 centimeter. By using photogrammetric tools or processes, we were able to create and generate the 3D meshes, the texturized 3D models, and digital surfer models, and of course the orthomosaics. So in terms of 3D modeling, we created 3 different 3D visualizations, 3 different scales. One scale was the island scale, the Placas Park scale, and of course the fossiliferous site scale. So in terms of island scale, we used the official cartographic product of Lesbos Geopark, which was a map that contains all the fossiliferous places that exist in the island. So we have the idea to use this kind of approach as the first stage where the visitor goes when he is using the application. So here you can see the cartographic approach, where at this time was only depicted this park, Placas Park in Sigri. We used the official map symbols for the 3D visualization, and as you can see on the right, this is the official map that was used to cover the surface of the island. So in terms of the VR application, we created 3 virtual spaces. The first virtual space was the space of the island scale. The second was the park, the entry to the park. And the third virtual space was the west part of the park with a specific teleport path where the visitors can follow and visit the fossiliferous places. So here you can see on the first virtual space, the 3D visualization of the Lesbos Island by using the official map and symbology. Of course, we have implemented information about the relative information about the geopark, and of course for the legend. Regarding the second virtual space, we have entered the visitor is entering to the Placas Park entrance, and has 4 triggered items: the info board, Placas map, and 2 paths. So we try to embed to this application cartographic products as maps. So because we strongly believe that the map as a visual and navigation aid will be very, very helpful to the visitors in order to to be teleported and to be, let's say, select the fossiliferous places and visit them and see the beauty of the tree trunks and the fossiliferous, let's say, remains of the trees. So you can see that there is a use of this map as a visual aid. So in terms of fossiliferous places, we have the first version view observation, teleporting inside the path, and the visitor can trigger information for this place, and also can see very close on first person view the 3D models of the fossiliferous trees on scale 1 to 5. So why we try to combine this kind of data to immersive geovisualizations? Because we believe that this kind of geovisualization, they offer unprecedented opportunities for experience and exploring geosites. They are transcending the physical barriers by democratize the access on geosites and by diverse audiences. So we strongly believe that these are new ways for interpreting, visiting, experiencing geoheritage and, of course, other cultural heritage places, and by facilitating interactive communication from the cultural heritage study areas in general. So are there any advantages? Of course, is the ability to observe sites across different scales simultaneously, from your house, from your desk, and you can see very detailed 3D models, which is a very promising approach by creating immersive 3D geovisualization. So yeah, that's for me, and I think that we can pass to our last presenter, which is Savas, and Savas will present us how VR and AR experiences breaking space and time in cultural heritage organizations. So the floor is yours. Okay, Savas, the floor is yours.
Hello, can you hear me? Okay. I'm Savas Martimianis. I'm from EO&GEO Solutions. I will present you Breaking Space and Time VR and AR Experiences and Visualization in Heritage Organization for Immersive Interpretation and Engagement. Okay. I will give you some definition about break space and time, overcoming the physical and chronological boundaries that limit how we access, experience, and interpret the past. Immersive technologies like VR and AR allows us to revisit lost places, compress centuries into moments, and immerse ourselves in other worlds beyond the limitation of museums, books, or ruins. Virtual reality is a fully immersive digital environment that replaces the user's real world surroundings. Augmented reality is a technology that overlays digital content such as images, sounds, 3D models, or text onto the real world environment through devices like smartphones, tablets, or AR glasses. So how we present now the culture. There is in the museums, and there is a static presentation of space. They have physical displays, dioramas, and models that recreate environments or scenes but all these things are not. There are also some architectural limitations. Space in the museum is finite. Only a fraction of a site or a collection can be displayed. There is also the linear interpretation of time. There is a chronological timeline. Exhibits often follow a strict historical order most of the times. Now museums, they're changing a little bit of that, presenting history as a single uninterrupted narrative. There is a lack of simultaneity. It's difficult to show how different cultures, events, or interpretation overlap or coexist in time. Also, here you can see a picture of how most of the museums present the artifacts. The visitors are observers, not participants. It's primarily text-based labels, and you just go in and read things. You don't have emotional or sensory engagement. It's a limited personalization, one narrative fits all. There's little flexibility to adapt to different interests, background, or learning styles. What is the challenges of representing the past is that the historical record is fragmented, there are incomplete remains, there is missing context, artifacts are often detached from the original use or meaning people cannot understand. There are some histories and of marginalized groups like women, children that are not presented, they're absent. There is an inaccessibility of the sites and the objects. There are geographic barriers. There are sometimes conversational needs. There is restricted access. Here we can see a picture that the Hagia Sophia changed for a museum and became a mosque. That changed the way that people visit this monument. There is also complexity of time and culture. The history is not, it's non-linear. The cultures involved, there are multiple interpretations. There's also audiences that struggle to connect with how we show in the traditional way the artifacts and history in a museum or in another place. There is a need for engagement and relevance. The younger audience, they want more interactive, more meaningful experiences. They want to learn. They are always on their phones, or they want to get to the museum the knowledge through the phones or through the technology. So we have to see how we evoke curiosity, emotion, personal connection. What VR and AR can do different, they can reconstruct lost or incomplete works, like inaccessible sites or destroyed sites, temples, palaces, ancient sites. They can enables users to experience environment as they once were, not just as they are now. There is a collapse time and enable the VR and the AR can users can time travel. They can travel through time and see the things in different historical periods. AR can overlay historical layers onto the present day landscapes, showing before and after comparison of the evolution of the space of a space over time. So also traditional exhibitions were not interactive. VR experiences are interactive, not fixed. Users can choose their own path through a narrative, or they can go freely. There is also sound, motion. Sometimes you can touch things like with haptic technology to create a deeper emotional engagement. Or even we can go to embodied immersive experience with VR, where you can believe that you are walking, or you're wearing the glasses and you're walking to a Roman forum, or participate to the rituals, or hearing voice of the past. AR can situate these elements in real world contents. You can lift your tablet and see things getting live. You can engage diverse audience in new ways. So tourist students can have a different approach. You can add also gamification, and so it can be more interactive. And with the gamification, people can learn more, and they have a curiosity, and they become active participants in the interpretation. Also, AR allows augmented local landscape to become with visible history to get live. VR can give a window to sites that are fragile or are closed, like an underwater shipwreck or a sealed tomb. And also, sense of being there. Yeah, you can connect with with the site or the museum or the artifact, you can feel that you are there by wearing. You can visit Louvre from your house. Here is a virtual reconstruction of Palmyra city that was destroyed. Part of them was destroyed during the Syrian civil war in 2016. We can see it, how it was. Some of the part is visual reconstructions. I can show you some use cases that were developed here in EO&GEO Solutions. It's the assassination of tens of Venizelos. Eleftherios Venizelos was the prime minister of Greece, and he had an important role in how the political things went in Greece. We designed the virtual space of the places where the assassinations were. I can show a video, maybe?
Yes.
Okay, I will show you. You can see the presentation and see the videos. They are very. Also, we designed a VR world of the office of Nikos Kazantzakis, a famous writer and philosopher of Greece. We reconstruct the office of Nikos Kazantzakis. You can, in Adibs, where he lived in France, you can touch the elements. You can talk with Nikos Kazantzakis, and he can tell you his story about when he was living in Adibs and what he was creating, about his writings, about his friendships, and all about his life. As for AR, we have designed here in Heraklion, in the Heraklion Museum, an AR application that gives lives to the artifacts. Here you can see an old vessel with an octopus graphic, and if you go with the AR application, you can see the octopus moving, and you can learn things about the vessel and about the vase and its use. And also here we have made Piraeus architectural walk, where in a map you can walk to the architectural monuments of. There are many architectural buildings that have a significance in architectural in the architecture. So you can see them, and you can in a map, and you can see information about the architecture. And you can see some 3D. The same is here about AR exploration at Fortezza in Rethymno, where you can lift your phone and see in sketches how, and we can see how it is now, and we can see how it was in the past, and we can add the things that are missing. And here is another AR application about the Battle of Samos in 1824, where you can see in the map how this battle that was in the water, how the ships were moving, and how this battle in the sea took place. And also you can see some of the old ships that were take part in this battle, and what they had inside. You can see it in your room, in your own table, and you can zoom out, you can turn them, and so you have a very nice experience. So there are some challenges, some limitations, ethical consideration of how you use VR and AR. There is a risk of historical distortion. People that are designing all the things and can make speculation. They can. There's a presenting a single authoritative narratives that overlook complexity and diversity, and history and archaeology is not so complex. It's complex. It's something complex. Also, there is oversimplification for entertainment. People and companies and others try to gamify or dramatize history so they can have many people to see to take all this information. And also there's whose story gets told. There is a bias about which is the primary narrative. Often local communities and some minorities are not referred in these applications. So also there are some ethical questions about virtual repatriation of cultural objects or spaces. And there's a big problem about accessibility to all these applications. The VR applications are high-end and are expensive and requires some infrastructure. Now there are the VR glasses that that the cost is falling, and so maybe this will solve the problem, but this is not always able to be done. Also, there is user data and privacy. Where all the data, all these things go that they collect, you just put in your personal data in this VR application. So they must be taken into account. And how you maintain all these applications. Application can be done, can be very nice, but sometimes the technology gets too much. It grows too fast that maybe in 6 months everything is outdated. So this is something that we have to figure out. Also, when we design the VR and AR applications, you can see we have to follow some meaningful, some principles and practices. It can be user-centered design. We have to build about the audience needs, the learning style, the emotional connection, include opportunities for exploration, choice, and interaction, ensure accessibility for diverse users, including children, elderly, and people with disabilities. There is also about the narrative depth, how much we get into the storytelling, what we say, how we say it, and how people receive all this. We can use historians, archaeologists, and community members to co-create the content. There is also integration with the physical space in AR, seamlessly overlay content on real-world environments. Replicate and enhance actual location with narrative context, dynamic elements, and atmosphere. We have to make the atmosphere right. Use sound, lighting, movement, so we can evoke empathy, curiosity, and wonder. And so we have to collect the feedback about what people see and always improve our application so we can make it better for all and easy for all. So we'll finish here with the future directions. It's the mixed reality museums. It's another thing that will come, and it's already coming. It's wearing these glasses, and so the glasses are getting smaller. The new meta glasses will be like you wear glasses, like the sun glasses. So this will be easy for anyone to not. It will be still expensive, but it will be more easy. So people can move to real space, wear the glasses, and so this will be a better experience. And also AI is creating different things. We can have also will help AI to easily update all the AR and VR applications and add things about the user behavior, the language and the aids, take account all this in the design of all the new applications. And also we can do more about the feeling, how you feel this experience, and make it more better, give to emotion, to the feelings, and to the empathy and the memory a lot. So for closing, I will show you this. This is designed from the Cleveland Museum. The Cleveland Museum is one of the best museum in new technologies. Everything happens there.
The story of the Cleveland Krishna. Right now, you should be seeing our title screen particleize into moving dots and be hearing the sound of a Cambodian flute. And now we present the story of the Cleveland Krishna.
I am Krishna, the miracle performing, flute playing god from India. Long ago, my legend traveled across the seas to Cambodia, where artists of astonishing skill carved my image in 2 stone sculptures, larger than life size. Today, I will show you the story of how one of them reached Cleveland, Ohio. The sound of my flute will guide you between 5 different stations, each 90 seconds long. Let's go! Walk with the sound of my flute to Cambodia, where the story begins. Here in southern Cambodia, a small sacred mountain with 2 peaks rises out of the floodplains. Today, it is known as Phnom Da, or Stone Mountain. 1,500 years ago, some of my devotees set 2 sculptures of me into cave temples, halfway up the slope. They are broken now, but they show me in the posture of holding up a mountain, which is something I did when I was 8 years old. Why did I do that? Well, it was like this. A raging storm was destroying our village. I lifted up the nearby hill called Marco Garden and held it like a great umbrella. This is the first time my people realized that I am more than just a special kid. They saw me as an incarnation of God.
This application is the future. You saw an empty room in a museum. There was an empty room, so you can do things different. They can be the story of Krishna. They can be another story. They can be any story that the museum can create and present. Thank you very much.
Thank you so much for your very interesting presentation regarding the use of AR and VR, and of course for the interesting examples. So on this side, we have finished our presentations, and I think that we have one question for Professor Skarlatos, for Dimitris, from an anonymous attendee. So he's thanking you, Dimitris, for interesting, comprehensive presentation. So he or she has the curiosity regarding satellite bathymetry. So he or she asking you if you have any examples of work to report, and could be there any methodological solutions to increase the accuracy of these computations. So Dimitri, I don't know if you can hear us.
Yes, I can hear you. Well, there are publications. Can you hear me?
Yes, Dimitri, we can hear you.
Okay, you can start from, I suppose that our presentations are going to be available, or no? Okay, I can write here some literature references that you can start looking forward. The accuracy depends on the satellite resolution, A, and on the satellite spectral dynamic range. It is not perfect, but it is a solution. So the difficult thing is having data to start training a satellite-derived bathymetry, because you need some kind of data to analyze, to give the algorithms. So for this kind of spectral reflectance, this is the depth, so that the algorithm can start. There are several approaches on that subject. I'm sure you will find a lot. Athos Agapiou has a publication on that for Limassol. And I can give you some more from Panagiotis Agrafiotis. Usually this works quite well when you have sandy bottom, or a bottom without any color, without texture, because textures like rocks and sand, and then again rocks with seaweeds, etc., makes the model more complicated. But nowadays, with machine learning, there are other approaches that further help you get depth out of satellite images. Okay, thank you. I will write here some publications, okay?
Okay. So I have another question from Ms. Nafsikandriou for Savas, Mr. Martiniadis. So she's asking, considering the tactile feedback in VR and AR relies on inherently limited actuators, how effectively can it replicate the nuanced complexity of real-world touch, and which specific methodologies are advancing this sensor illusion?
Okay. And this is a big problem, how to collect the data from the people that are using you're right, all the VR applications are in the museums. Maybe with the metaverse, maybe all these applications, maybe all this VR can be uploaded in the meta world or the other world that are developed now, and so we can collect from there all the data that we need so we can make the applications better.
Okay, thank you, Sava. So since we don't have any other questions, I think we are at the end of our workshop. So I would like to, before we close, I would like to thank all of today's presenters for their excellent contributions. They give us an overview of various geoinformatic technologies and how we can use them in real case studies. And of course, for cultural heritage monitoring and mapping. I would also thank our audience for the engagement, for the questions, and I'm hoping that this participation will spark new ideas, let's say, for and potential collaborations. And thank you once again, all. Of course, we would like to thank MDPI and Mladen that are hosting us. Thank you very much. We will be in touch for probably a new version of our workshop since we have more. And we're looking forward to welcoming you to our future events that will be released in a few months. So thank you, Mladen.
You're very welcome, Dr. Papakonstantinou. Thank you. Thank you, and thank you all to our speakers for their participation and for their efforts to make this webinar successful. And thank you all for joining us today. And we had the privilege to hear some outstanding speakers, I can say, and who showed us how geospatial technologies and different tools could help us to better understand and preserve the cultural legacy that we have. And again, sincere thanks to all of the presenters for sharing the expertise, for sharing their work, and I would like to thank you to the audience for their time, interest in, and some good questions they asked. Again, special thanks to the journals team, to our marketing team, of course, for making this webinar possible. And we hope that today's presentation sparked some new ideas and potential collaborations. And we encourage you all to stay connected with the community. And please do not hesitate to contact us or speakers if you have any questions. And until next time, take care, and thank you very much for being the part of this webinar journey.